Hello, everyone. This is Group 6 Senior Design Team from University of Central Florida, and today I'm going to talk about the Huddy Buddy. It is a heads-up display, and it is the heads-up display, the HUD, that will be your bud when you get into mud. I am Pedram Nafisi.
I'm Logan Glove.
I'm Aaron Magidly.
And I'm Evan Hall.
All right, so let's talk about the motivation for this project. Usually when you're driving in your car and you're either using your built-in GPS or you're using your phone as your GPS, generally if you want to look where you're going, you're going to have to take your eyes off the road. And there are off-the-shelf solutions that fix these sort of things, but they're really just reflecting your phone screen off of your windshield, and so the reflection is going to look like it's only maybe a foot or so in front of your windshield, and even though it's overlaid with the outside world, you're really not able to see the road in front of you. We also wanted something that wouldn't require any permanent modification since we were going to be testing it in our vehicles. And we wanted something that could use our knowledge from our different disciplines. So our goal is to design a heads-up display that would give up-to-date GPS directions from a known reliable mapping service. We wanted it to work with a wide variety of vehicles, so we wanted to use the OBD2 ports for getting its data, and we wanted to use GPS-enabled Android phones to get the GPS data. We wanted it to be safe, so on top of allowing you to focus on the road in front of you, it also has a crash detection system. We wanted it to be cost-effective, and we wanted it to leave a positive impression on the user. All right, so for our specifications, we try to keep it pretty simple, basic, and reliable. So for the size, we didn't want it to be too big. So for our largest enclosure, it's going to be 9-inch by 5-inch by 2-inch. We didn't want it to be too heavy because we don't want it banging around too much. So it has to be less than 3 pounds. We wanted a wide temperature operating range of -20 Celsius to +60 Celsius because, you know, cars can operate in those temperature ranges. We wanted it to be able to work and be stored in direct sunlight because sunlight's a pretty hard environment to work in. We wanted the power consumption to be kept pretty low just so that it wouldn't affect the user's vehicle too much. We were going to use the OBD2 port both as a data connection and for power. We wanted it to work with Android devices since Android is so common. We were going to use the Mapbox API because it's free and open source and it has a lot of documentation. Our connectivity standard will be Bluetooth 2.0 plus EDR. It's very common and very well documented, and it doesn't use a whole lot of power. For our display, we're using an OLED screen because they're widely available and there's a lot of documentation for it, as well as they have amazing contrast. The resolution we're using is 128 by 64 pixels. It's not the best, but we're still able to use it to read the directions. And we wanted the whole system to have adjustable mounting because, you know, every car and every person's different. All right, so for a block diagram, we have a list of the different steps that are taken and who was responsible for designing those steps. So for all of the power delivery, that would have been done by Evan. All of the optical design work would have been done by myself. A lot of the programming would have been done by Logan and Pedram. And some of the extra programming for things like the backup safety system were done by Logan and Evan. All right, so now to get to the basics. The Mapbox API is feeding information to the Android app, which then connects to our display. And the display is also receiving information and power from the OBD2 port. So on one feed, we're getting all the navigation data, and on the other feed, we're getting power and things like the vehicle speed and even the fuel consumption. So the different subsystems are the display unit, which consists of the OLED display, lenses and mirror, and the overall housing for it, an ATmega 2560 microcontroller, a SIMCOM SIM808 2G GPS module, an ADXL 335 accelerometer, an OBD2 power source with a backup battery, the PCB development, our custom-made Android application, and the HC05 Bluetooth module. So when we were originally coming up with this, we really wanted to focus on having a sunlight readable display. And so what we were originally looking at was a transparent LED with a very bright backlight. The transparent LCD that we were looking at was the ENH DG128064-66. It's a bit of a mouthful, but what it gave us was a very compact transparent LCD that we can then stick a diffuser and a very bright, system-controlled LED. The problem was it uses a very unique connector, and we weren't actually able to get it to work with any of our systems. In fact, we had a hard time finding connectors for it. So we went to something that was a little more proven and a little easier to work with, the Seed Studio Grove OLED. It's similar size, it has the same resolution, it uses a much more common protocol, and it only uses 4 pins, so it's a lot easier to work with. It has amazing contrast, which is really useful because now only the lights that we turn on will be visible in the reflection, and we can control it directly from brightness. So the basic idea of our lens system is we have our OLED display, and then a negative lens, or a concave lens, that'll kind of spread the image out. But that also has the effect of creating a virtual image just in front of the OLED display that's a little bit smaller. And that is going to be placed at the focal length of a larger positive lens. And with that virtual image at the focal spot of the positive lens, that means that the image coming out of the other end of that lens is going to be collimated or focused at infinity. This is what's typically done with the heads-up displays that you'll see in aircraft, where the image is focused at infinity. So if you're looking at a car, say 100 yards or more ahead of you, that image is still going to be in focus. All right, so for the information that we wanted to display, we wanted to keep it informative but simple because we're only working with 128 by 64 pixels. So we wanted to include the speed and fuel consumption data from the OBD2 board of the vehicle. We wanted the navigation data from the Mapbox API via the Android app. And we wanted the microcontroller to send the data to the screen over a serial connection. All right, so for mounting the device in the vehicle, we were going to design an enclosure that has a way to not be permanently affixed to the vehicle, but it's going to hold tight. And we wanted to be able to make it adjustable to account for height differences in instrument clusters and in shape, height, and angle of the windshield. And we wanted to keep it inside the driver's field of view.
All right, so to kind of take all of that data from all of those different sensors and other components, we wanted to select a microcontroller that was suitable of handling that much data, that much bandwidth. So the two options we came up with were the Atmega 2560 8-bit microcontroller and the Texas Instruments MSP 430 F447 16-bit microcontroller. Both seemed to be fit for the job, but at the end of the day, we ended up going with the Atmega 2560 due to its open source schematics. So we were able to pull in the schematics from different vendors and use those in our implementation of our custom PCB. It has 54 pins of I/O, which is great for all of our individual components. 16 analog pins, which is perfect for our accelerometer. A 5-volt operating voltage, which means it can be powered by the OBD connector. 256 gigs of flash storage, which is perfect for large-scale programs like ours, and a 16 megahertz clock, which is great for high-speed applications. The Atmega is also very popular for embedded and robotics projects. So one thing that sets our project apart from other off-the-shelf methods is its crash detection system. The microcontroller uses the accelerometer to detect large changes in forces. We read in the data for gravity relative to the X, Y, and Z axis on the accelerometer. And if a large change is detected by the microcontroller, it will initiate an emergency response sequence. So if that occurs, the microcontroller issues AT commands to the cellular 2G model, 2G module. It will retrieve the current GPS coordinates and then send a text message containing those coordinates to a designated emergency contact. In the event of a power loss due to the large forces in a crash, maybe the car shuts down, we had a backup battery take over to ensure that that emergency response was received by the emergency contact. So here's a little overview of how that would work. The Huddy Buddy requests the GPS data from the satellite once the accelerometer reads a high force. The satellite will return the GPS data to the Huddy Buddy. The Huddy Buddy will send the SMS containing the GPS coordinates to the SMS network, and then it will eventually reach its SMS emergency contact destination. So the cellular 2G module that we set out with was the SIMCOM SIM808 GSM 2G cellular module. We had looked at the SIM5320 3G module, but it turned out to be a little bit more expensive, and it wasn't as durable as the SIM808. It's a quad-band GSM GPRS module with GPS for satellite navigation, US cellular via SIM card, and we're currently using Ting Mobile as our service, which leases network space through T-Mobile and other established cellular services. It uses the AT command set implementation, receives the commands via UART. The external GSM GPS antennas are on the board itself, and it has a 3.4 and 4.4 volt supply voltage. So the accelerometers that we wanted to choose, we wanted to make sure that the forces could be read accurately. So it became either a ADXL 335 3-axis or a ADXL 337 3-axis accelerometer. We chose with the plus minus 3G of the 335 due to the testing parameters for the higher sensitivities required a much larger force to actually register, which we didn't really feel like subjecting ourselves to that kind of G-forces, so we went with the lower sensitivity one. So to pass that on to Evan now for the power delivery.
So there were a couple options when we were first looking at power delivery. The first one was we were looking at the cigarette port lighter. And later we were looking at the USB ports. And finally we came to the conclusion that the OBD2 port would be really cool to use, because not only does it supply the 5 volts and delivers up to 2.1 amps, we are able to take in additional data from the car sensors and display them to our OLED screen. So most of the components are driven off of the 5 volt input, but there's a couple peripheral parts that require more or less voltage needed to operate. So there were buck and boost converters used. The LM2577 was initially supposed to be used for the LED backlight, and it was going to supply up to 9 volts at 800 milliamps, but it's no longer required since we're not using the LED anymore. But also I had to swap out a part, the LD1117S50TR, instead of the other one listed there. The other one that's listed was on the Arduino schematic, and it is not readily available, so I had to go find a new voltage regulator, and this one has slightly better dropout voltage and better current handling. So being a beginner with PCB development, there's plenty of software out there for creating your own PCB, such as Altium, there's OrCAD, there's Eagle. I ultimately went with DipTrace. DipTrace became very easy to use. I felt like it was a lot like Multisim. One of the drawbacks, and I'm sure it's for the other softwares as well, is they don't always have part schematics for every part that's out there. So there are online sources that allow me to go in and download footprints and use them in my schematic, or they make it very easy to just create your own if you want to do it that way. The supplier for most of the components that we're using for the PCB came from Mouser.com, with 1 or 2 coming from Adafruit and DigiKey. And the actual vendor for the PCB was JLC PCB over in China. So here is just a quick schematic of the Atmega 2560. the SIM 808, and finally the ADXL 335. This is the final product of the PCB development. Go back. So up here, you can see that this is going to be the input power source. Down here is the backup battery pins. And this was going to be for the photodiode that, again, was a good idea back when we were going to use the LCD screen. But once we switched over to the OLED, we found out that it was not able to do contrast settings. And then these pins here are for the OLED itself. You can see that this is the ATmega, the SIM, and this little tiny guy is the ADXL. Down here is when we were actually having to push our sketches onto the ADXL. We used an Arduino Uno as a bootloader, and these are the pins that allowed us to push the sketches onto the ATmega. And then finally back here is the SIM holder for the Ting SIM that we were using to send text messages. So you're probably going to get tired of hearing this, but once COVID hit, there was a lot of delays. There was a ton of setbacks. So being beginners in soldering and PCB developments, I mean, the pins on the ATmega and the SIM and even the ADXL are really small. So a huge shout out to Quality Manufacturing Services. They helped us a lot. They were very kind, and they allow college students to give them their senior design projects, and they help put on the more harder parts for us. We had an initial board that we were testing, and the turnaround for that was like a day, but when we came to our final board, it took 2 weeks for response, a couple more days before I was finally able to get the board down to them, and it took almost a full week for them to get the final product back to us. And another issue was time. So once I got the final board back, me and Logan started testing it, and it really stunk because on our first revision, the SIM was not connected because of a PCB footprint error. So the SIM wasn't drawing any power whatsoever. On this one, the SIM was connected, and there is an inductor for the LM2577, too low of a current rating, unfortunately. I think it was rated at like 400 milliamps. The SIM must have used in excess of 300 because I believe the ATmega was only pulling 100 when we began testing. And it just totally burnt the inductor, and we weren't able to continue testing on our final PCB, unfortunately. Some of the things we were able to test was the backup battery system. So in the event of a crash and there's no power being supplied from the OBD2 port, the backup battery is two 18650 size battery cells, which give a total of 7.2 volts to continue powering the entire board. Basically, a blocking diode is keeping it shut off while the full 9 volts is still on. Once the 9 volts drops, the 7.2 kicks in and is still able to supply the components needed to send out the text message. This is a very simple layout of how it should work. You got the 9 volts going through a diode, and then you have the 7.2 going through that blocking diode. And once the 9 volts is shut off, the 7.2 kicks in, and that 1 kilo ohm resistor is just there to kind of simulate the load, which was the LM2577, which converts the power back down, or I'm sorry, the L1117, which converts the power back down to 5 volts.
All right, so for this display enclosure, we wanted something that would be able to hold the lenses that we wanted to use and the mirror that we wanted to use just the right distances from each other so that we can get that collimated image. Normally, this is something that could have been machined out of a material like, say, Delrin or even aluminum if we wanted to. But due to current events, we had to go a different route. We ended up getting these parts 3D printed. And that was pretty nice because for designing the parts, we could just punch in the number that we wanted and we would get the size that we wanted. And then it was just a matter of getting the parts printed and putting them together and then dropping our different optical components into it.
All right, now I'm going to talk about the parts external of the Huddy Buddy, which is the app and the Bluetooth portions of it. So for app development, we decided to go with Android and using Android Studio with Java as the programming language. Kotlin, which was the alternative, was also a very valid way to code this up. However, due to the prior backgrounds of the programmers and them being familiar with Java, we chose Java. We chose Mapbox for API calls rather than Google because Mapbox is free and open source and Google has certain terms and conditions that prevented us from using their services. And the app is here so that you can choose the location you want to route to also be able to check the Bluetooth status and as well as designate the emergency contact phone number in the case of a crash. Here you can see two different Bluetooth modules that was considered. Originally, we were going to be using the NRF52840, and it uses Bluetooth Low Energy and has Nordic SDK environment. It is smaller than the HC05 and it's a bit more expensive, but ultimately we chose the HC05 as the Bluetooth module of choice due to it using Arduino as its development environment and making it easier to combine with the other Arduino components, and as well as the fact that it uses Bluetooth 2.0, which although is no longer Bluetooth Low Energy, is merely one step above in terms of performance and constraints, and is still fit well between all the constraints needed.
All right, so for the testing of all of our individual components, we kind of did it by subsystem. So the microcontroller was tested using Arduino sketches for each component. So the SIM808 utilized the Adafruit phono library. The ADXL335 used some of the Adafruit accelerometer functions. The OBD2 Freematics UART adapter used the Freematics OBD2 library, and the Grove OLED display was capable of using the U8G2 display library. After all of these components were individually tested to confirm their functionality, we then combined them into one sketch, and we were able to successfully pull speed, fuel economy from the OBD, detect a crash on the accelerometer to get the emergency detection over to the emergency contact with the current GPS coordinates of the Huddy Buddy.
All right, to continue on with the testing, for the HC05, we had an Arduino Nano to connect it to a computer, and we used this in order to use a phone to send messages to the HC05 and then read back the messages sent to the HC05 via serial, and that was the point of the Arduino Nano. And then for the Android application testing, we use just the Android Studio IDE as well as a Google Pixel emulator to check functions on a computer, and then a Samsung Galaxy S8 for physical testing.
All right, so and then with the custom PCB, we use the Arduino Uno for the bootloader to load up the sketches onto the PCB. We connected the OLED to the PCB, which then we supplied 5 volts to the PCB to power it on. We could then disconnect the 5-volt mains power supply to test the backup battery, and then we used a photodiode to print out the light values for the module.
All right, and for our optical system, the way that we tested it was by grabbing a few different mounts so that we're able to hold the display, the smaller concave lens, and the larger convex lens lined up together. And we had done work previously to figure out the correct spacing for it, but there's more than one way to space it out. And so we tinkered around with it a little bit until we got the crispest, or the most crisp image that we could.
So here we can see the work distribution of our team. There are multiple overlapping areas between us all, and everyone was kind of in cahoots with each other at all times, just talking back and forth, and everyone helped out with each other. So for financing, we are not a sponsored team. So all of this, the money for all the parts came out of pocket. And because of this, we carefully logged our budget initially and then calculate how much it ended up afterwards. And if we could use free tools and free resources, we went for them. So this is a budget screen. This is the estimated cost of all of our parts, and all of the parts are listed here. And the bill of materials here is how much everything actually costed, as well as the vendors where we got everything from. And as you can see here, the total came out to $392, which is a bit under budget, so that is a good thing.
So some of the challenges that we experienced with this project primarily was dealing with the consequences of COVID-19. A lot of the parts that we had originally planned on using were delayed from China, which caused us to seek other options, as well as remote work between all of us. Two of our students were affected by the early stay-at-home orders by Orange County, which affected how much we could sort of get parts to each other and working, in proximity with each other. As well as affected the ability for quality management services to aid us in the custom PCB development. We had an issue selecting a display that would give us a high enough brightness for daylight operation. It turns out that OLEDs are not the brightest in terms of being able to compete with the sun. We would love to move to a much brighter implementation, but with the timeline and the scope for this project, it was much more realistic to stick with the OLED. We wanted to ensure compatibility with a wide range of vehicles and smartphones, which led us to make decisions with the OBD2 and the Android module, but we would like to open it up to iOS eventually in the future. Making sure that we had the correct 3D printed part sizing was also an issue. We had to get a couple revisions of the mount, but once we had that, we were good. We also had some unexpected issues with some components, specifically the SIM5320 3G module that we originally planned on going with was not as durable as we would have liked it to be, as well as the configuration of the SIM808 with the OBD library and the software debugging. So that is the Huddy Buddy project for the electrical, computer, and optics and photonics senior design for Group 6.